This is the first video in a series of videos on circuit analysis. If you're taking my course, then you will want to have read the syllabus already. Now, before we get into the material proper, for all of my EE courses, I like to put the course in its proper context. And so I want to give the entire spectrum of the subject of EE and where this course fits in. So before we do that, let's talk about an abstraction. Okay, in an abstraction, for example, let's say I had an object here. Here's the object, and I apply a force to the object. Okay, there's the force, and I ask you, what is the acceleration of this object? What would you say? Yeah, you'd say, tell me what the mass is. Give me the mass of the object, and then I can tell you what the acceleration of the object is. And so in doing this, you have ignored many properties of this object. For example, you've ignored maybe it's got a certain color. Okay, you've ignored the color. Maybe you've ignored any magnetic properties, any electrical properties. You've ignored the shape of the object, its density, and so forth. And that's because some smart guy has come before you and has written down this equation, and so you know that if you're given the force and you want the acceleration, all you need is the mass. That's an abstraction. The abstraction is that you've ignored all of those other properties, and you have used a law that has come before you, and so you can start right there at that law. Okay? You don't need to know how this law has come to be to answer the question. That's an abstraction. All right. So the EE spectrum. First, all the way over here on the left, there's nature. So imagine you wanted to build a circuit and you were going to connect some voltages to some things and you were going to measure the current. Well, all the way over here, before any abstractions have been set up, there are no rules or anything for which you can design by. And so maybe you've got a potato, and and the potato represents, of course, just some electrical device, and you don't know how this thing behaves. So there are no rules. So you just start connecting some voltages, maybe 8 volts, and you measure 0.1 amps, and maybe you connect 6 volts, and maybe you measure 0.2 amps, and so forth. And again, there's nothing for you to design with there, and so this is all you're limited to. But of course, there's an abstraction there. People have done this already. So this vertical line I'm drawing here, this represents an abstraction. People have done this, and scientists, physicists, okay, have done this already. Experimental physicists. So over here now, the new abstraction is physics, and so we have Ohm's law, for example. We have Maxwell's equations. Okay, and along with that, then of course there's Faraday and Gauss and Ampere. Okay, Ampere's law, Faraday's law, Maxwell's equations, and so forth. So now here we've got the equations that govern what you would do or what you would expect. You don't have to just connect things ad hoc in an ad hoc manner. You can predict them with physics. Okay, so here's a new abstraction, and we don't necessarily just want to use the laws of physics. For example, if we have a light bulb and we connect a certain voltage, we don't want to have to calculate the current and the electromagnetic field, in and out of the light bulb using Maxwell's equations. And so this next abstraction, I'll just write LCA here, and I call this the lumped circuit abstraction. Lumped circuit abstraction. Lumped circuit abstraction. So here we can put all of the physics that's happening inside a device, and we just write the device, for example, like a capacitor. And we just give it a circuit schematic symbol. And maybe we don't know what's happening inside the capacitor, but we can start from this, and we can connect that thing to a circuit, and we can investigate what happens externally to the capacitor. Or we can take a voltage source. And a DC voltage source, like a battery, has a lot of complex chemistry things happening inside of it, and physics will dictate that, and maybe we're not interested in exactly what's happening inside it, but we want to connect our battery to something and be able to figure out what's going to happen externally to the voltage source, and resistors as well. Maybe we're not too concerned with what's happening inside the resistor, but we want to know what's happening externally, and so that's our abstraction. Now from here, from the lumped circuits, we can build amplifiers. Amplifiers. And the schematic symbol for an amplifier is this kind of triangle looking thing. So an amplifier will have these kind of components inside of it, okay, but it's possible to start at the abstraction of the amplifier. Just how does the amplifier work externally? Now from the amplifier there are two directions to go. We'll go to the top here first, and then we'll come to the bottom later. After the amplifier, you can start building digital logic gates. For example, an inverter or an AND gate. Okay, you can build those logic, and the other ones too, NOR, NAND, exclusive OR, and so forth. And then from the digital logic gates, you can combine these logic gates, which we call that, of course, combinational logic. Combinational logic. And so these things will take some inputs, and they'll do some sort of higher level function, higher level, and have some outputs. If you took a digital course, you know that that's not the whole story. You can use combinational logic to build a sequential logic or a clocked circuit. And start to introduce memory into your circuits. So here's our clock input, and you can synchronize a digital system and so forth. The idea is, as you go from left to right in this spectrum, things should be getting simpler for you. Now you're controlling a digital system without having to just build things in an ad hoc manner and try to guess what's going to happen, right? So you don't have to do that because the physicists came and they gave you some laws. Then from that we are able to lump all these things into some circuit symbols, and then from that we can build our amplifiers, and all we have to do is analyze the amplifiers. From that, all we have to do is analyze the logic gate, and so on. Now after here, after the clock circuit, I'll call this ISA for instruction set assembly. So this is like assembly language. Assembly language. This is really not taught in engineering schools too much anymore. This is programming language. I forgot an A there in language. This is programming at the ones and zeros level. And it's really tedious. So, and not extremely useful, so it's not really taught too much. But what is taught is a higher level programming language. Programming language. It's not programming at the ones and zeros level, of course, but a higher level, for example, C or MATLAB or Java. Okay, and the idea is, again, your life should be getting simpler as we go here. So now you're using words like for and while, and you're controlling a computer, and that gets turned into ones and zeros in the instruction set assembly. And those ones and zeros control a clocked circuit, which is made up of combinational logic. And that combinational logic is made up of logic gates and amplifiers and transistors and so forth. So now this is, your life again is getting simpler as we come over here. Now you can also then, with your programming language, you can build upon that with software systems. Software systems. Okay, this is like Linux or Unix or DOS, and so on. And then after that, this is where the money is here. And you can build important things like video games. Okay, not just video games, of course, but things where you don't have to be an engineer to understand. That's the idea. Things have gotten easier. You don't need to know the physics if you've done all of this correctly. And this is where you make the money. So this is where you're able to turn your knowledge of electrical engineering into money, because you can market things. Because things have gotten easier, you can build and market things for the average person who does not know physics or engineering. So this is the digital path up here. But parallel to that is the analog path. So if we come back down here to amplifiers, we can build things called op-amps. Op-amps are these amazing little devices with magical little properties. I won't say too much more about that. But from op-amps, you can build a lot of different analog system components. Analog system components. So here we would have things like power supplies, oscillators for communications equipment. That's coming next. Oscillators, filters, all of this good stuff here, and you can use that to make money. And that's where you would build your control equipment or your communications equipment. And of course, these two paths here, they are not mutually exclusive. I put equations, equipment. They're not mutually exclusive. Most applications require both the digital and the analog. So where are we in this class? Well, we are right here. This series of videos will cover this abstraction, perhaps just a little bit maybe into this amplifiers, and we'll reach back a little bit, especially at the beginning, into our physics. Okay, but mainly we're going to be concentrating here in the lumped circuit abstraction. Great. And I'll, of course, delete or clear the whiteboard as we move along, but you're encouraged to pause the video if you choose to do so, if you want to do so. Okay, so now let's say I have a copper wire here. Here's my copper wire. And let's say the two ends are connected to something. So I'll put those dots there, the ellipses, just to show that it's connected to something, but we're not too concerned with what is connected just yet. And let's say that in this copper wire is a current flowing. Now in this course I'm going to assume that we have to start somewhere, and I'm going to assume that you know a little bit about voltages and a little bit about currents. That is, you've taken Physics 2, or you're at least in Physics 2 now, and definitely I'm going to give an analogy here in a second to Physics 1, and I will have assumed that you've taken Physics 1. So in this copper wire is a current, let's say, because it's connected to something. So there's current moving in this copper wire. So what is current exactly? Well, current is the movement of charge. Current is the movement of charge. And so you know that there are two kind of basic things that have charge. That would be the electron and the proton. So in a copper wire, or in anything that's carrying charge for that matter, what is it that's moving? Is it the electron, or is it the proton, or is it both? It's the electron. Electrons are moving in this copper wire. That's because the proton is heavy relative to the electron, and it's bound to the nucleus. The electrons are lighter, and a copper has one valence electron. A valence electron is electrons that are easily dislodged from the atom, and so it has one valence electron, which makes it a good conductor. And I won't say too much more about that. But let's say in this copper wire, electrons, I'll draw an electron here. Okay, let's say electrons are moving this way, right, down the wire. So, if electrons are moving from right to left, this end of the wire is becoming more negatively charged. Right? Because the electrons are moving to the left. So, what about this end, the right end? That's becoming more positively charged. Because the electrons are leaving. Electrons are leaving there. So, mathematically, it's equivalent to saying that positive charge, and I'll draw not a proton, but just positive charge, is moving from left to right. Because if we had just positive charge moving from left to right, then this would still be true. The left would become more negatively charged, and the right would become more positively charged. Physically, of course, that's not what's happening. Okay? We know that the electrons are moving from right to left. But mathematically, it's equivalent to saying positive charge is moving from left to right. Why that's important is because current is the movement of charge. Okay? It's actually current I is the derivative of charge, Q, with respect to time. And we don't always want to be worrying about the negative sign of an electron. The electron is what's moving. We don't want to carry through this negative sign. So our perspective is going to be that actually positive charge is moving from, in this case, left to right. And so current, I, is actually moving this way. That all of this is to say that current always moves in the direction opposite of electrons. Good. So that's current. What do you know about voltage? V. Well, voltage is what gives the charge the potential to move. And it's an electrical potential energy. Electrical potential energy, okay, in joules, okay, normalized by charge. And that gives us 1 volt. So this is, we'll say 1 volt. 1 volt equals 1 joule divided by 1 coulomb. Coulomb is the measurement of charge. So up here for current, current is measured in amps. 1 amp is 1 coulomb divided by 1 second. Okay, so it's back to voltage. A voltage is an electrical potential energy normalized by charge. Electrical potential energy. So you've dealt with potential energy from physics. Okay, gravitational potential energy. Here I have a simple experiment just to remind us all about gravitational potential energy. So I've got a track with some grooves, and I've got a marble, and I've got some blocks on either side of the track. Okay, and I also have some extra blocks here too. I've got 4 more extra blocks. Okay, so actually if we remove the blocks from both sides, right, I've got this, and if I put the marble on one end, of course the marble does not roll. And that's of course because both ends are actually at the same height. Okay, so there's no potential difference there to make the marble roll down the track. Right? Now if I take 1 block and I put it on one end of the track, right, of course if I let the marble go, it rolls down the track. This guy is 1 block or 1 unit of height, and this guy, this end, is 0 units of height. Now, what if I put 1 block here? So now both are 1 unit of height high. Okay. Well, perhaps it's not exact. My table here is not exactly level, but if I put the marble does not roll. Right? So you say, well, raise the height. Okay, well, let me take 1 more block over here and 1 more block over here. Will the marble roll? No, it doesn't. That's because even though this one is now higher, right? It was 1 block and now it's 2 blocks, but this one is also higher. It was 1 block, now it's 2. The difference is still 0 blocks. There's no potential difference there. Alright, let's go back to the case where it did roll, okay, which was when I had 1 block here and 0 blocks here. We do that again. Okay, the marble rolls down no problem. What if I raised both ends by 1 block? So I'll put 1 block here and I'll put 1 block here. What will be the speed now of the marble compared to just the last experiment? the speed is actually the same. The speed is the same as when there was 1 block here and 0 blocks here. Why is that? The reason is because it's the difference in heights that matter. It's not the absolute height, okay, whatever that means. It's not the number of blocks, it's the difference in blocks. If I wanted to make the marble roll faster, then I need to increase not the number of blocks on this side and this side, but I need to increase the difference in the number of blocks comparatively. So if I wanted to increase the speed of the marble, well, let me just put 1 more block over here and leave this side alone. Now the difference in heights is 2 blocks, and the marble rolls down faster. In this analogy, the ramp, or the track, is a resistor. And again, I'm going to assume that you've seen resistors, at least in physics 2, and the circuit schematic for a resistor, its symbol looks like this, R. Okay, the ramp is a resistor, and you know Ohm's law, V equals IR. That is to say, the voltage is equal to the current times the resistance. They're proportional. The voltage and the current are proportional to one another. So if you have 0 current, then you have 0 voltage, and vice versa. Now resistors can be component resistors. Okay, these are the ones that you see in lab. They look almost like a cylinder, a very small cylinder. They have 2 leads, and they have different colored bands. Okay. Those are component resistors, and there are also load resistors. So load resistors are the prizes at the end of the maze. Load resistors are your ultimate goal. You're trying to, you're building a circuit for some reason. You want to give some voltage to something or give some current to something, and that something is the load resistor. So this would be like headphones, for example. Headphones are approximately resistors in that if there's no current through headphones, then there's no voltage across headphones. And if there's no voltage across headphones, there's no current through headphones. That is to say speakers, right? Speakers. And speakers are such that the voltage and the current are proportional to one another. Okay, appliances like washing machines or dryers or toasters. Okay, appliances are roughly resistors in that the voltage across them is proportional to the current through them. And light bulbs, of course. Okay, load resistors. They're the ultimate goal. That's why we're designing a circuit, is to deliver some sort of current or some voltage or power to a load resistor. And the component resistors help us change the voltage or the current in a circuit. Okay. So if we're keeping with a maze, the component resistors are kind of the changes in the maze. Here's the start. And we go through this maze, and we ultimately get to our end prize, and here's the load resistor. Okay, so back to our ramp analogy. The ramp is the resistor, and the number of blocks, okay, remember there were blocks on either end. Those blocks play the role of the voltage, because the blocks are ultimately changing the height, which changes the gravitational potential energy, and the voltage, as we said, is an electrical potential energy. So come back to this equation here. Oh, it's such an easy equation, right? So easy. Mathematically, it's very simple, but students interpret this equation incorrectly often. The resistance is usually given, so that's 1 kiloohm or 10 kiloohms or 1 ohm or 10 ohms. There's no confusing R in this equation. The current, well, there's really no confusing that either. The current is the current that travels through the resistor. I is the current traveling through the resistor. No really mistake in that. The issue in this equation is, what is V? Is V the voltage on this end, right? This is going to have some voltage, V1, and this end is going to have some voltage, V2. So in this equation, is V the voltage at this end, or is V the voltage at this end? Well, think back about the analogy here. What determined how the marble rolled down the track? Was it the number of blocks on one end? Was it the number of blocks on the other end? Or was it the difference in the number of blocks? That's the same thing in this equation. And V here, this is Ohm's law. V is not the voltage at one end. It's the difference. It's always the difference that matters in the electrical circuits. It's always the difference in voltage. Think about your gravitational potential energy problems. The first thing you did was set y equals 0 somewhere to solve these problems. You set y equals 0. And it didn't matter where you set y equals 0, because it was always the difference in heights that mattered. The same thing here. In fact, we can set v equals 0 anywhere in our circuit, and it's the difference that's going to matter. Okay, back to the analogy. So the blocks is the voltage. The marble, that's positive charge. Positive charge. The speed of the marble. Do you know what that is in this analogy? The speed of the marble is the current. Remember, the current is a rate of change. It's that rate that the charge is flowing, right? So the speed of that ramp, or the speed of the marble is the current. So, coming back here to our circuit, if we want more current, then we are going to have to increase the voltage difference across that resistor. Now, also from physics, you've seen voltage sources. A voltage source looks like this. Let's say, for example, 3 volts. And its job is to fix the voltage at this end, the positive side, to be 3 volts higher than the voltage at this side, the negative side. Okay, here's our resistor. And let's say there's another voltage source over here. And the 2 voltage sources are connected. So we'll make this 3 volts. Question: how much current is going through that resistor? Well, what's the voltage difference? See, here, down here is the table. Okay, this is what the blocks have in common, this table. So now this side goes up by 3 blocks, if you like, and this side goes up 3 blocks. So what's the difference in the 2 ends? 0. So in Ohm's law equation here, for V we would put 0. So what's the current? The current is also 0. What if we wanted a current now? Well, we would have to change the voltage difference. Right? We'd have to change it to, let's say, we can change one of the ends if we like. We maybe change this end to 1 volt. Now there's a voltage difference. Okay, this side is higher than this side. So in this equation, the difference is 2. So in this equation, Ohm's law, we would put 2 volts in for V. Now back to our analogy, actually. Back to our analogy. Here's my ramp. Here, I guess that's the blocks. Here's the ramp. Here's the blocks on the other end. The marble goes down. The marble always goes down from high potential to low potential, right? It goes down the ramp. Never, never up the ramp. All right. Now, in this analogy, then, we would say that the ramp is absorbing energy. And related to energy is power. Power is the time rate of change in energy. So you've got the marble rolling down the ramp, and there's some friction there, and the marble goes from high potential to low potential, and the ramp is, of course, absorbing energy through friction. Imagine if you place the marble at the low side and it rolled up the ramp. Well, in that case, the ramp would have to be some sort of active device where it's supplying energy and it's supplying power to get it up the ramp. Okay, but that's never the case for a simple ramp, right? Well, that's not the case ever for a resistor either. A resistor never supplies power. That is to say, the current in a resistor never flows from low potential to high potential. Never. So, in our circuit here, the current direction, here's 3 volts, here's 1 volt, the current direction would be this way, I. And let's give a value for the resistance. Let's say that's 1 kilo ohm. Okay, the current from Ohm's law then is 2 volts equals I times 1 kilo ohm, and that makes I 2, what's the unit? Milliamps. So when you divide by kilo, 10 to the third, you get 10 to the minus third milli. So the magnitude of the current is 2 milliamps, and the direction is from left to right, high potential to low potential. Now, it's the whether the device here, the resistor, is absorbing power or supplying power, this is actually can be made more general. Let's take any device, and I'll describe that device with just kind of this black box. So now we're not saying there's a resistor in here. There could be a voltage source, or there could be a current source, or whatever. There are a capacitor, inductor, transistor, whatever. But it's a device, okay, and it has 2 terminals. And there's a difference. Call that V. From this top terminal to this bottom terminal, we're measuring the difference there. And there's a current flowing. Call that I, measured from top to bottom. Now, if V is positive, That is to say, if the voltage at the top is larger than the voltage at the bottom, and current is positive, that is to say the current is actually moving from top to bottom, then that device, even though we don't know what's inside, we can say that thing is absorbing. It's absorbing power. Because the current enters the high potential and leaves the low potential, just like in this ramp where the marble starts at high potential and leaves at low potential. Now let's say we measured the voltage across there and we actually got something negative. But the current was still positive. Okay, if we measure a negative voltage from here, top, to here, bottom, then that actually means that the bottom is the higher potential. And if current is still positive, then current is still going from top to bottom. So now here, current is entering the low potential and leaving the high potential. That's the equivalent of the marble going up the ramp. So in this case, that device is supplying power. And I'll let you work out the other cases. There are two other cases here. You can think about those other cases. Now, the question might be, how much power? How much power is the device supplying or absorbing? Well, if you look at the product of V and I, okay, if you look at the units of that product, so we said voltage was in energy, joules, divided by a charge, coulombs, times, and we said that the current was a charge, coulombs, per second. Then the coulombs cancel, and you're left with joules per second. Joules per second, a rate of energy, that's a watt. Right? So power, electrical power, is I times V in watts. So this tells us how much power, but it only tells us the magnitude of the power. It only tells us how much power. It doesn't tell us whether it's absorbing or supplying. We have to deduce that from the circuit. We have to use reasoning. Well, is the current going from top to bottom? Is it going from high potential to low potential, and so forth? This tells us the magnitude of the power that that device is absorbing or supplying. And there's something called the passive sign convention. Sign convention. Okay, and what that is to say we are going to we're just going to assign positive power, okay, positive power we're going to assign to when something is absorbing. When something is absorbing power, we're going to just make it positive, and negative power negative power is when something is supplying power. And algebraically, it works out then, as you'll see in some examples later on, that the power supplied equals the power absorbed. That is now, because we make one positive and one negative, when we add all of the powers and all of the components, we will algebraically get 0. Okay, so let's take a look at, let's stay with this example here. And let's calculate the power in these 3 devices. Okay, so the power in the resistor, well, I times V. So we said that the current was 2 milliamps. And the voltage across it is 2 volts. So this makes 4 milliwatts. And because the current enters the positive side of the resistor and leaves the negative side of the resistor is absorbing power. Resistors always absorb power, and so that's positive. The passive sign convention. We're just going to make that positive. Now the power in the 1 volt source, okay, well, that 2 milliamps has nowhere to go but through the source. So the power through that source, or the current through that source, is 2 milliamps. The voltage across it is, of course, 1 volt. That's what a voltage source does, is it fixes the voltage across it. So when I do that multiplication, I get 2 milliwatts. And here, notice, this is the positive side. Okay, and this is the negative side. Notice the polarity of the battery. So the current enters the positive side, leaves the negative side. That's also absorbing power. Yeah, you might not have guessed that because it's a power source. But yes, power sources can absorb power. You charge batteries, right? You can charge batteries. So yes, this power supply here is absorbing power. So we're going to make that positive. Then the power in the 3 volt source. Okay, well, that current has nowhere to go but through the 3 volt source, so that current is also 2 milliamps through this guy. And the voltage across it is 3 volts. So if I do that multiplication, I get 6 milliwatts. And here, the current enters the negative side and leaves the positive side. So that's the marble rolling up the ramp. This thing is supplying, so we're just going to make it negative. You see what I mean when I said that this equation only gives you the magnitude of the power? You have to reason through whether you should tack on a negative sign or not. Now, notice here when I add up all of the powers, that's 4 milliwatts plus 2 milliwatts minus 6 milliwatts. This is a closed system. It's a closed circuit. I get 0. That means that the power supplied is equal to the power absorbed. Okay, just one more thing, and that is nodes and loops. And we'll stick with this circuit for now. This circuit has 2 nodes. This is a node, and this is a node. Oh, excuse me. Nope, let me back up. This circuit has, 3 nodes. This is a node, this is a node, and this is a node. Let me define nodes for you. Okay. A node is the entire wire separating at least two components. Okay, so now you see this guy here is the entire wire. We'll call that node 1. Node 1. Node 1 is the entire wire that separates the 3-volt source and the resistor. Here's node 2, we'll call it. Node 2 is the entire wire that separates the resistor and the 1-volt source. And node 3 is down here. This is the entire wire that separates the 2 voltage sources. Right, so let me draw you a different circuit. See if you get the idea. Let's make a different circuit over here. So 1 volt. So 1 ohm. 3 ohms. 6 ohms. 1 ohm. Okay, take a look at this circuit. Can you correctly tell me how many nodes are there in this circuit? If you want to pause the video, go ahead. But the answer is 1, 2, 3, 4. 4 nodes. Okay, this circuit has 4 nodes. You can label them if you want. Okay. 4 nodes. And a loop is a path such that an electron can start and end without backtracking. Okay, the first circuit over here has 1 loop. So if you imagine an electron is here, maybe the electron goes this way, okay, and it comes back at this point, let's say. So it starts here, and it comes back here, and it did not backtrack. All right, this circuit, I'll draw the loops in red. This circuit here has how many loops? It has actually, if you guess 2, you're not right. There are 3 here. Here's 1 loop, kind of the small rectangle up top, and here's another loop, a small rectangle at the bottom. But another path that the electron can take is the big rectangle here. That is a 3rd loop. Now let's use what we've learned to go through some examples. Okay, so as we go through the examples, you kind of want to work these out for yourself. Go back, look through the video to see if you can get the answer before I solve it. So, for example, let's say we have some component in this black box, and the voltage here at the top relative to the bottom is 2 volts, and the current moving in this direction is 3 milliamps. Okay, I could ask something like, is the device supplying or absorbing power? Okay, and of course, how much power? How much power? Again, pause the video if you'd like. So the solution is, first of all, P equals IV. This gives you the magnitude of the power. So, in this equation, I is the current through the device. So that would be 3 milliamps. And V is the voltage across the device. So that's 2 volts in this. This guy, we don't know how much voltage this guy is, but it's 2 volts higher than this guy. So that's 2 volts. So the power here is 6 milli watts. That's actually the answer to part B. For A, we have to ask ourselves, is the current leaving or entering, is the current entering the positive side or the higher potential? If the current's entering the positive side and leaving the lower side, negative side, then it is absorbing power. So that's exactly what we have in this case. Right? The current started here at the higher side. Notice the polarity. This is 2 volts higher than this side. So this is the side with the larger number of blocks, right, in the marble analogy. So the current starts here, current goes through the device, comes out the lower potential, lower side. So that device in there had to absorb that power. Okay, let's try another one. Okay, and this one's going to be worded a little bit differently. Let's say you know that the left side of this thing is at 3 volts, and you know that the right side of this thing is at -1 volt. And you measure the current going from left to right as 2 amps. Okay, and we want to know the answers to those same 2 questions. Is the device absorbing or supplying power, and how much power? Okay, A. Notice the current is positive, so the current is indeed moving from right to left. If the current was negative, that would mean it's actually moving left to right. So the current is moving from right to left. Now we look at the voltages on either side, -1 and 3. Well, 3 is larger, so the current is moving toward the higher potential. So it left the lower potential, and it's going up to the higher potential. The marble is moving up the ramp. So this thing, that device, whatever it is, it's not a resistor, but it is supplying power. So how much power is the question now? P equals I times V. Alright, well, I is easy. That's the 2 amps. V, it's always the difference. It's not about how many blocks are on this side. It's not about how many blocks are on this side. It's the difference in the blocks. Okay, so we have 3 volts here and -1 here. So that is a difference of 4 volts. So that makes 8 watts. That device is supplying 8 watts of power. Okay, now, you say, well, you know, should I put negative there? Well, we already answered the question that it's supplying power. So, I mean, you can leave off the 8 watts. You can say it's supplying 8 watts. Or you could just algebraically just say -8 watts. Either way is fine. Alright, let's take another example, more concrete example. Let's say we have a 9-volt battery here, and we have a 10 ohm resistor here, and a 5 ohm resistor here. And we'll say a 1-volt source there. Okay, question. For this circuit, we'll say how many nodes are there? How many loops? And yeah, we'll stick with that. How many nodes, how many loops? So for this guy, remember that the nodes are the entire wire separating components. So here's 1 node. Here's 2 nodes. 3 nodes. 4 nodes. 4. How many loops? Well, there's just 1 loop there.